Okay, so the next thing I want to talk about is the delta method. Right? The delta method is another valuable tool we have for asymptotic distributions. So what the delta method says is that if, and now this is a given, or part of the theorem for the delta method, so it's not what the delta method says, but if we have that square root of n, y sub n minus mu converges in distribution to a normal 0 sigma squared, which is a form of the CLT, right? Then, for a function g of x such that, two criteria, g of x is differentiable, and 2, g prime evaluated at mu is not equal to 0, we have that the square root of n of g of y sub n minus g evaluated at mu converges in distribution to normal with mean 0, variance is g prime of mu squared times sigma squared. Or, rewriting that, g evaluated at y sub n minus g mu all over the absolute value of g prime of mu. Notice it's absolute value because we're taking the square root of something squared. Times sigma over square root of n converges in distribution to normal 0, 1. I like the top one better. I think your book likes the bottom one better, but really either one. I mean, they're equivalent. So an example for that, right? If xi's are IID Bernoulli parameter p random variables, then we know by the CLT that x bar minus p, because expected value of xi is equal to p, right? Over sigma over square root of n converges in distribution to a normal 0, 1. Right? Which, rewriting this using another form of the CLT, this gets us x bar minus p all times square root of n converges in distribution to a normal 0 sigma squared. Notice sigma squared for a Bernoulli random variable is p times 1 minus p, right? So then we have square root of n, x bar minus p converges in distribution to normal 0, p 1 minus p. Okay, so that's just setting up the delta method. We haven't actually applied the delta method yet. So if we have a function g of x, so let's say g of x is equal to ln of x over 1 minus x, right? This gets us that g prime of x is equal to 1 over x plus 1 over 1 minus x, which is equal to 1 over x times 1 minus x. Then we have, by the delta method, finally getting to use the delta method, square root of n times ln of x bar over 1 minus x bar, because we're plugging in x bar to our function g of x, minus ln of p over 1 minus p, because we're plugging in our p into our function g. And this converges in distribution to a normal random variable with a mean 0 and variance equal to 1 over p times 1 minus p all squared. Notice we're plugging p into our g prime of x and then squaring it, right? All times p times 1 minus p. You can actually cancel out one of the p's, 1 minus p. So this is equivalent to normal, mean 0, and variance is 1 over p times 1 minus p.